We are in chapter 2 where we are discussing strain. This is the 12th session overall and the 4th session in strain. Here we discuss stress concentration and theme of investigation of axially loaded members and deliberation on further analysis. This is a map of the sessions covered in the first 4 chapters. We are now in session 12. Here we look back and we look forward. We look back at what has been covered in the first 2 chapters. We focus on issues that will be covered not only in chapter 3 and 4 but later on. Here we discuss Saint Venant's principle and stress concentration. First, we look at Saint Venant's principle. First and second chapter, we have often considered a bar subjected to axial loads. We have also generally considered the distribution of stress perpendicular to the axis of the bar to be uniform. However, as mentioned earlier, this is not always the case. If we consider a section perpendicular to the axis near to the point where the load is applied, the stress distribution will not be uniform. The problem of determining stress at this section is a statically indeterminate problem. It is solved by using mathematical theory of elasticity. Now consider a small column with end plates. Compressive forces are applied through the end plates. The plates are in contact with the column, but otherwise the connection is frictionless. Under the loads, the column will shorten and expand in the lateral direction. It is considered that plane sections will remain plane. Strains will be compatible with end conditions and will be uniform. As such, stresses will be uniform in a perpendicular direction to the axis. Now, consider this plate, which is a thin plate of width h and are tensile forces acting as shown. The stress distribution here will be quite different from the case we just discussed. For a start, we can see that the deformation where the load has been applied will be much larger and the deformation at the corners is zero. Now here the adjoining elements must be continuous in their deformed shape. Elements will deform by equal amounts on adjoining sides. Given that the deformation is not uniform, the stresses will also not be uniform near where the load acts. Now consider a perpendicular section at a distance h by 4 from the edge. The stresses in the center are quite high and the stresses near the edge are low. Sigma maximum by sigma minimum here is 13. Consider another section at h by 2 from the edge. Here sigma max by sigma minimum is more than 2. Stress variation has become more even. Now consider a perpendicular section at a distance h from the edge. As we can see here, the stress distribution is nearly even. This is Saint Venant's principle. According to Saint Venant's principle, for an axial load or any other load applied over a small area, we can treat it as a statically equivalent system at a distance from the ends of the member approximately equal to the width. The distribution of stress here will follow a simple law. In the case of axial loads, the law is P by A. The distribution is independent of the loads, of the way the loads are applied at the edge. Here we discuss stress concentration. In the last slide, we discussed the case of a bar subjected to tensile loading. The stress around the point where the load was applied was found to be higher than other parts of the bar. So we can say there was a stress concentration near the point where the load was applied. If bodies have discontinuities, such as a hole or a change in width, then there is stress concentration. The stresses near the hole or where the width changes is higher than the rest of the plate. In design and analysis, we need the maximum stress applied to a body. Regions of discontinuities with stress concentrations can be areas where the maximum stress occurs. The maximum stress divided by the average stress is referred to as stress concentration. Stress concentration is denoted by K. Hence, in this equation, if we know the average stress and if we know the value of K, we can find out the maximum stress. Determining K is often difficult and the photoelastic method is used. Tables and graphs such as figure A and B have been created for different bodies which give the value of K. Stress concentration factor does not depend on the material or the dimension such as D. It depends on the ratio of the radius of this hole to D or R by D. So consider a plate where R by D is 0.2, R by D is 0.45. Then the K is 2.2. This means that the maximum stress is 2.2 times the average stress. Now, if the thickness of the plate is D, then the average stress is given as P by dt, where P is a small d. This is a case where the width of the plate changes. The stress concentration factor depends upon two geometric ratios, B, that is big D by small d, and the radius of the fillet divided by small d, that is R by d. So consider a case where the capital D by small d is 1.2. So this curve, and the radius of the fillet divided by small d, that is R by d, is 0.2. Then as we can see, the stress concentration factor is 1.6. So the maximum stress would be 1.6 into average stress, where the average stress would be given by P divided by dP, where P is the thickness of this plate. It is to be noted that the stresses obtained using the stress concentration factor has to be less than the yield stress, since we have used Hooke's law. Here we reflect on the theme of the investigation involving actually loaded bars and deliberate on further analysis. Till now, we have discussed a fair bit on normal stress and strain and shear stress and strain and corresponding attributes. However, that is not the focus of our discussion here. The focus is on the scheme of investigation involving actually loaded bars. This scheme serves as a blueprint for other investigations, such as investigations involving torque, moment, and shear. Here we'll mainly discuss how we investigate torque and moment based on what we have learned so far. Thus, the theme of the investigation is discussed in an integrated manner, consolidating what we have learned till now. So these are the three cases. We have already considered axial force acting on a bar. We took a section perpendicular to the axis and found out the stresses. Okay, here is a circular bar subjected to torque. We'll similarly take a perpendicular section, is a section perpendicular to the axis, and find out the stresses. This is a beam subjected to both moment and shear. So if we take a perpendicular section here, then that section will be subjected to moment and shear. Load here is considered to act on the axis of symmetry of the beam. Mainly discuss the investigation involving bending moment in a beam. Here we look at bars subjected to axial loads in an integrated manner using the treatment of circular members subjected to torque and beams subjected to moments are in the same vein, and we'll look at them briefly. So for a bar subjected to axial loads, we initially find the magnitude of the axial loads. We then take sections perpendicular to the axis of the bar and find out internal forces. The stresses in these sections are uniform, and the normal stress can simply be given as the load divided by the area. If the bar has sections with different axial loads and different area, then we find out the maximum P by A, or the maximum applied stress. We then compare it to the maximum allowable normal stress to check for failure. We have dealt with cases where the maximum allowable normal stress was given, and we had to move in reverse to find out the maximum external axial force. Using Hooke's law, from normal stress, we can get normal strain. Writing Hooke's law as a force displacement relation, we can get elongation. Elongation is the deformation in the case of axial loads. If a bar has portions where either P, E, and A vary, then we need to separate this portion to find elongation. So we separate the length into portions with constant P, E, and A and find their elongations, and then sum it up to find the elongation of the whole bar. Now let us consider a circular bar subjected to an external torque. As before, we can take sections perpendicular to the axis and find out the internal torque using the method of section. The way shear stress has been given is more involved than this straightforward case. A formula has been derived to give shear stress in a section subjected to torque. Now, depending upon sections and the internal torques, we can find out the maximum applied shear stress. We can then compare it to an allowable value and check for failure. From shear stress, using Hooke's law, we can get shear strain. We can see from here physically that when a torque is applied, it will twist the circular member, and we can find out the angle of twist. In this case, this beam has been subjected to a load only, but beams can be subjected to loads and moments. If we take a section between A and C, then it will be subjected to both bending moment and shear force. However, here we look at bending moment only. Determining normal stress from the internal bending moment is again more involved than this straightforward case and is given by a formula. Knowing the internal bending moment at any section, we can find out the maximum applied normal stress. We can then compare the maximum applied normal stress with the maximum allowable normal stress to check for failure. From normal stress, again using Hooke's law, we can get normal strain. In bending, the normal strain is related to deflection. So we can find out the amount of deflection. In the next slide, we'll look at failure, which is applicable to all the three different types of loadings. After that, we'll look at finding internal forces in the case of torque and moment. We then briefly touch on stress strain in the case of torque and moment, and on deformation in these two cases. So here we have given a partial overview of the topics. We get a feel of the unified nature of the subject, and this will help us anticipate the discussions as we go forward. Here we compare stresses to an allowable value. In the earlier slide, we discussed stresses. These stresses need to be compared to an allowable value to prevent failure. Bodies subjected to forces can fail in different ways. The different manners in which bodies can fail are grouped under theories of failure. Theories of failure will be studied later. In a way, we have already used two of the theories of failure when dealing with forces, bars subjected to axial forces, and components subjected to shear forces. These two are normal stress theory and shear stress theory. To understand normal stress theory, we need to remember about principal stresses. Consider this to be a member subject to two different loads and such stressed at all points. Let A be a point in the member. Let us consider an element at the point A and rotate the element keeping in mind the variation of normal stresses. After a full rotation, the maximum normal stress that acts on the element is noted. This maximum normal stress is called the principal stress. Let us now consider all the points in this member. Let us rotate all the points and find out the principal stresses acting at all the points. We can then find the absolute maximum principal stress acting on the member. According to normal stress theory, the member will fail when this absolute maximum principal stress is equal to the ultimate stress. As the element at point A rotates, we can also find the variation of shear stress. After a full rotation, we can find the maximum shear stress acting. Similarly, we can consider all the points and like previously, we can find out the absolute maximum shear stress that acts in the member. We can then compare the absolute maximum shear stress to an allowable shear stress. This is shear stress theory. We have earlier mentioned that we have already used the normal stress theory. So now we'll show how we have used the normal stress theory. This is a bar subjected to axial load, and we have taken a section perpendicular to the axis of the bar and found out the stresses acting. An element aligned with the section, when considered, is subjected to only one stress, which is sigma x, and is given as P divided by A. We now rotate this element at different angles. We found that the normal stress is less than P by A at all the different angles. So P by A gives the principal stress. If we take perpendicular sections at other points in the member, we'll find that the principal stress is the same as this principal stress. So this is the absolute maximum principal stress in the member. Earlier, we dealt with this principal stress and compared it to the ultimate stress. We also used normal stress theory in a form when we compared this stress with the maximum allowable normal stress. The general procedure discussed here is also applied in torque members subjected to torque and moment. In those cases, the normal and shear stress theory is also used. As earlier mentioned, we'll take a look now at internal forces in circular bars subjected to torque and beams subjected to transverse forces. Obviously, we'll study internal forces in more detail when we study torque and moment. The discussion now is only to show the integrated nature of the topics. Here we discuss the method of sections applied to a circular bar subjected to torque. This is similar to method of sections applied to a bar subjected to axial forces. So here we have a circular bar ABCD, to which a torque P1 and torque T2 are applied. You can see that there must be a torque at D so that the whole bar is in equilibrium. Let us now consider section MN taken perpendicular to the axis of the bar. Then since the whole bar is in equilibrium, the portion to the left of MM will also be in equilibrium. However, we see that there's no force acting on the portion left of MM. So there will be no internal torque acting at the section MM. Consider now another section perpendicular to the axis NN. Now again the whole circular bar is in equilibrium and the portion to the left of NN, considering internal forces, will be in equilibrium. As we see, there's only one torque applied at B. So the section at NN must have a torque T1 applied in the opposite direction for equilibrium. On the face of the right-hand portion, there will be a torque T1 acting the opposite direction to the left-hand face. So these two torques on the left-hand face and the right-hand face form an action-reaction pair. We can take another section OO and again considering the equilibrium of the portion on the left of the section, we can see that there are two torques, T1 and T2 acting. So for equilibrium on the section OO, a torque T1 minus T2 must act in the opposite direction. Here we consider the case of a section of beam subjected to moment only. Normally, a portion of the beam would be subjected to both moment and shear. So this is the beam AB. Two point loads must be applied to the beam, both at a distance A from the edges. Since the loading is symmetrical, the reactions at A and B are both P. We now consider a section perpendicular to the axis of the beam, MM. Then, since the whole beam is in equilibrium under loads, the portion of the beam left to MM will also be in equilibrium considering internal forces. The portion of the beam left of MM is shown here. We can see that there's a force P acting upwards and there's a force P acting downwards. So at the section MM, there's no shear force required for equilibrium. However, a moment will be required for equilibrium. Here at the section MM, there's a moment Px due to the reaction at A. And there's a moment in the opposite direction Px minus A due to this load. So the net moment at section MM is Px minus A is equal to Pa, where we have taken clockwise moment as positive. Hence, for equilibrium of this portion, since there is a moment, there has to be an anti-clockwise moment, Pa. Instead of taking the left portion of section MM, we can also consider equilibrium of the right portion of MM as shown here. Then we will find that there's a moment acting at the section and its direction would be opposite to that of the left portion. These two moments form an action-reaction pair. Now, if we consider a section at NN and consider the left-hand portion of NN for equilibrium, we'll find that at the section NN there's a moment PA as well. The direction will be the same as the section MM. So between C and D, the moment remains equal to PA and there's no shear force. Here we have a case of a beam where at an internal section there is both moment and shear acting, unlike the previous case. So this is a beam to which a load P is applied at the center. The reaction at A and B would be P by 2. Consider perpendicular section O. Then if we consider equilibrium of the portion to the left, then there's a force P by 2 acting upwards. For equilibrium at the section O, there must be a force P by 2 acting downwards. So in that case, there is a shear force on the section O. Also, if we look at the moment acting at the section O, from the left side, we see that there's a moment Px by 2. So in order to balance that moment, there must be a moment Px by 2 acting on the section. So at the section O, there's both a moment and a shear force acting. There would be an equal and opposite moment acting on the right portion, and these two moments make up an action-reaction pair. Similarly, there would be an equal and opposite shear force acting on the right portion, and these two shear forces make up an action-reaction pair. In the case of axial force or torque, we needed to take sections at only one or two places. By taking sections at one or two places, we could give the axial force or the torque for the whole member. This is because the axial force or torque remains equal for a portion of the bar. This will not be the case if there's continuous variation, but we normally don't deal with cases of continuous variation of torque and axial force. Here, however, we see that the bending moment depends upon x, which is the distance of the section from the point A. So as we take O or sections in different positions, the bending moment will vary. The internal forces in case of bending moment are therefore represented in what is called bending moment diagrams, where the internal moment is given for the whole beam from A to B. This is different from torque or axial force. In effect, we are applying the method of sections to all parts of the beam from A to B. In the case shown here, the shear force is constant for a portion of the beam, but sometimes the loading has continuous distribution, and in such cases the shear force can also vary from the one end of the beam to the other end of the beam. And we also form shear force diagrams like bending moment diagrams. With bending moment and shear force diagrams, we can find the maximum bending moment and shear force acting on the beam. Here we discuss stresses as found from the internal forces. For a bar subjected to an axial load, the determination of stresses was found to be quite straightforward. The magnitude of the stresses could simply be given by dividing the force acting by the perpendicular cross-sectional area. For a circular member subjected to a torque or a beam subjected to a moment, the determination of stresses is more involved. To start with, we find the variation of strains using heuristic arguments. Once the variation of strains is settled, we use Hooke's law to find out the variation of stresses. These stresses would make up the internal torque or moment, and formulas are obtained of the torque and moment with the stresses. These formulas are equivalent to the simple formula sigma A is equal to P in the axial case. We now discuss deformation. For an bar subjected to an axial force, deformation is the extension or the reduction in length of the bar. For a circular bar subjected to torque, deformation is in the form of twist. For a beam subjected to transverse force, deformation is in the form of deflection of the beam. Finding extension or reduction of a bar subjected to an axial force was a straightforward case. From Hooke's law, we had sigma is equal to E into epsilon, which we could convert to a force displacement relation, and we got delta, the extension or reduction, as equal to PL divided by EA. In the case of a circular bar subjected to torque, from geometrical considerations, the angle of twist is related to the shear strain. In a beam, from geometrical consideration, the strain is related to the curvature, and the curvature is related to the deflection. So strain gets related to the deflection. Strains in both these cases are related to stress by Hooke's law, and the stresses are related to internal forces. Hence, just like the relation delta is equal to PL by EA, we get formulas which give the twist in circular bars subjected to torque and deflection in beams. However, determination of these formulas are more involved compared with the axial case.